Okay, so hello and welcome everyone to the second week of interactive live sessions for the course on computational fluid dynamics for incompressible flows. As you all know, this course is being offered by NPTEL and is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am the teaching assistant for this course. I am a PhD scholar at IIT Madras, and we shall be solving some problems together and discussing anything and everything related to the course. So, without any further ado, let's jump into the questions. So, the way it works is you read the questions, you find out the correct solution to it, and you can put in your response in the chat box, or you can unmute and answer as well. If you have any question, absolutely do not hesitate to ask. This platform is, the way we can maximize the utility of this platform is by having a two-way conversation between each other. The lectures are all one way. The professor teaches us and we just look at the videos. We can't really interact, but the main goal of these sessions is to complement that and have a two-way discussion on things related to the course. So every week we will be uh, looking at some new lectures related to a topic, and we will discuss them every week. So we will have 12 weeks of live sessions corresponding to the 12 weeks of lectures. So this is corresponding to the second week of lectures where we learned how to classify different partial differential equations, and question number one relates to that as well. It's asking us which of these is not a type of partial differential equation, PDE in short, based on their mathematical classification. So we learned two kinds of classification, physical and mathematical. So among mathematical classifications, which of these four options is not a type of PDE? Is it option A, circular, option B, elliptic, option C, parabolic, or option D, hyperbolic? We have one response in favor of option A, circular. Let's see what others have to say. Option A again. We've got two votes in favor of option A. Anyone else? Okay, so let's take a look at the solution. It is actually option A, circular. So the question was, uh, which of these is not a type of partial differential equation based on their mathematical classification? So as we learned, there are two kinds of classification, right? One is a physical classification and the other is a mathematical classification. So as it turns out that options B, C, and D, elliptic, parabolic, and hyperbolic, these are all types of mathematical classification. So the only odd one out is option A, which is not a mathematical classification, that is circular. So we also learned about two physical classifications as well. Can anyone tell me uh, which was the two ways in which we can physically classify partial differential equations? Feel free to unmute and answer, or you can type in the chat box as well, whichever way you feel comfortable. Physical classifications, which was the two? One was an equilibrium problem. What was the other one? Anyone? It was a time marching problem. So these are the two ways in which we can physically classify a partial differential equation problem. Anyway, so the answer to this question would be option A, circular. So moving on to the next question. Now see, we talked about time marching problems in the last slide and it came up in this question. So this question is asking us that in order to solve time marching problems, we require which of the following? Do we require option A boundary conditions? Do we need option B initial conditions? Do we need option C all of the above? Basically meaning A and B. Or is it option D none of the above? That we don't need any of these to solve time marching problems. Take your time, read the question carefully and pick out your correct solution from these four options. Okay, we have one response in favor of option C, all of the above. Let's see what others have to say. Option C again. So the question is, in order to solve time marching problems, what do we require? Do we require option A boundary conditions? Do we need option B initial conditions? Do we need option C both, that is all of the above? Or is it option D none of the above? So far we have got two responses in favor of option C, that is both A and B or all of the above. Let's see what others have to say. Okay, so let's take a look at the solution. It is actually option C, all of the above, that is both B and D. So time marching problems are also known as IBVP, the full form being initial boundary value problems. So let's say if this is my domain X, let's say if I'm interested in the domain of X being from 0 to L, and this axis is my time. So if I want to find out the evolution of a certain variable in time, I need to know the boundary conditions at both x equal to 0 at all times, as well as at x equal to L at all times, as well as I need the initial value at all x. So this is the initial condition I see, and we also need the two boundary conditions BC. So for solving time marching problems, we need both initial and boundary conditions. So the correct answer would be all of the above. Any questions on this or anything else? If not, we will keep moving along. We'll move on to question number 3 now, which is asking us that in order to mathematically classify partial differential equations, coefficients of which terms of the equation should be considered. So let's say in any general partial differential equation, the coefficients of which terms of the equation should be considered. Keep in mind that our main goal being to mathematically classify them. Is it the terms of the highest degree, or are they the terms of the lowest degree? Are they the terms of the highest order, or the terms of the lowest order? So just a quick refresher on the differences between degree and order. Okay, so we have already got one response in favor of option C. Two responses in favor of option C. Okay, so a quick refresher on the differences between degree and order. Can anyone tell me how do you define the degree of a term in an equation? So let's say I have this equation. Um, dou phi dou t cube. And this is dou 4 phi dou x's cube. So if this is my equation, my partial differential equation, what is the highest degree of this equation? Yes, correct. So Tushar wrote that the degree should be 4. And what is the highest order of the equation? 2. Are you sure? Okay, so let's take a look at the solution. It's actually option C, the terms of the highest order. Now going back to our example, so it's actually uh, the other way around. The order is 4. Order refers to the highest derivative. Order of derivative. And degree is the degree should be 2 here, and degree refers to the uh, the power, like degree. So the degree of this equation would be 2 because the highest multiple of any term that we take is power 2. So the highest power in a certain equation. So let's say if we now come back to the general uh, second order partial differential equation. So keep in mind second order, that's what we learned about. So what was that? We had a dou 2 phi dou x square plus b dou 2 phi dou x dou y plus c dou 2 phi dou y square plus d dou phi dou x plus e dou phi dou y plus sum f into phi plus g equal to 0, or we can write equal to g as well, doesn't matter. So the thing is, in this equation we focus on the terms of the highest order, so those are the second order. So that's why we will consider these coefficients. We will consider a, we will consider b and c. And as we learned that b square minus 4ac, the value of this particular expression is what determines how we mathematically classify the PDE. That if it's less than 0, then we'll say that it's elliptic. If it's equal to 0, we'll call it parabolic. And if it's greater than 0, it will be hyperbolic. So it's the highest order terms in a given equation that matters. So if we go back to this equation now, and let's say I have these two coefficients, a and b. Which coefficient will you consider for if you want to classify such an equation, a or b? Remember, we have to consider the coefficient of the terms of the highest order. B, correct, because this is the term of the highest order. This is a fourth order equation, fourth order second degree, right? Okay, so let's move on. Any questions on this? If you have any questions, please ask right now. Alright, so if there are no questions, we'll keep moving along. We'll move on to question number 4, which is a match the following type of question. So we have two columns, one on the left, one on the left and one on the right. So on the left column we have different physical equations. So the name of the the exact physics of the equation is mentioned here, but these we are familiar with the mathematical forms of these equations as well, and we will need those forms to determine which one is uh, a parabolic, elliptic, or hyperbolic. So let's try to match these options with one another, and then once you have figured out the correct combination, you can then pick pick it up from the options given below. So the options given below are A1 A2 C3, option B A3 B2 C1, option C A1 B3 C2, and option D A2 B1 C3. So let's try to write down the mathematical forms of the equation first. Please help me with them. So let's say the first one, a 2D steady state heat conduction equation. How would I write it? So temperature would be in T, and the um, the two spatial, let's write them in 2D because it's 2D. So the two spatial coordinates would be X and Y. So how to write the 2D steady state heat conduction equation? Can anyone help me out? Okay, at least tell me if I'm writing this correctly. So this is dou t, where t is time. Then I have dou 2t dou x squared alpha plus alpha dou 2t dou y squared equals 0. Is this correct or not? No. Why so? Which term should not be here? Steady state. So it shouldn't have a unsteady term, right? So this one shouldn't be there. So this is the 2D steady state heat conduction equation. So here we can forget about this alpha as well. So that's all. That's the equation. Then 1D unsteady heat conduction equation. In this one we will have dou t, right? And this should be equal to alpha dou 2t. Here we have only one direction, so the, only we will consider the second derivative with respect to x and not y or any other direction. So it's basically heat diffusion equation. And option C is second order wave equation. So the wave equation we have, I'm writing t itself. We usually use velocity for writing this, but let me use. This is usually equal to c square, then dou 2t, and this is in 1D, 1D in space. So that's the wave equation. Now we have to match this with option 1 parabolic, option 2 elliptic, and option 3 hyperbolic. So you can now quickly see if okay, we already got a lot of votes in favor of option D, but let's try to see how can we get to the solution. So option A is this one. So here our A's and B's would be A and C, and B would be 0, and these are both 1. So for the first one, B square minus 4AC, if I try to write, so B is 0 and A and C are both 1. So this is minus 4, hence elliptic, because it's less than 0. So the first one would be elliptic, A2. Then this is A. Then for B, we have to consider the terms of the highest order. So this is the one that we'll consider. And here A is alpha, and B and C are both 0. So for option B, while evaluating b square minus 4ac. B is 0, 4, then A might be alpha, but B again, C again is 0. So the value is equal to 0, hence it's a parabolic type equation. So B should correspond to 1 parabolic. The only other option remains this one, C should be 3, but let's confirm that. So for C we have, again if we consider A, B, C, so our C actually is C squared. Here this C is different, this is velocity of uh, the wave. So if we try to find out B square minus 4AC for this one, B square is 0, then we have 4 AC, so A is 1, and okay, and this equation should be written in this way, this being equal to 0. So C is actually minus C squared, so this would be minus C squared. This turns out to be 4C squared, and C is a positive quantity. C squared would definitely also be a positive quantity, so 4C squared is also positive, hence this should be greater than 0, and hence this should be hyperbolic. So my correct combination would be A2, B1, C3, which is option D, and that is the correct answer. So if you have any questions on this, please shoot them now. Okay, cool. So let's move along. We'll move on to question number 5 now. So this is the um, yeah, yeah. So this is the compressible inviscid flow equation. Here the m infinity is actually the Mach number. It's basically the ratio of the the fluid velocity to the speed of sound in that medium. But anyway, that doesn't matter here. We'll focus only on the mathematics. So mathematically, if I have to classify this equation, what should it be? So we have one response in favor of option D, and uh, also that it should be a function of the Mach number. So let's see what others have to say. So is this equation hyperbolic, elliptic, or parabolic, or option D, any of the above? Okay, we have another vote in favor of option D. So again, comparing with the general form. So comparing with the general form, this is A, B is 0, and C is 1. So if I try to write down what the determinant b square minus 4ac is, it should be 0 because b square is 0. Then we'll have 4 into 1, sorry, not 1, 4 into 1 minus m infinity squared, and c is 1, this being, so this being equal to 4 m infinity squared minus 1. Right. So if now we'll have multiple cases here. So if m infinity is exactly equal to 1, then the value of this determinant becomes equal to 0. And this equation turns out to be parabolic. So this is the sonic flow case, where the velocity of the fluid exactly matches the speed of sound. I can have two other cases. One is when m infinity is less than 1, then of course b square minus 4ac would be, or this one, m infinity square minus 1 would be negative, in which case we'll have an elliptic equation, which is nothing but a subsonic incompressible inviscid flow. And when m infinity is greater than 1, then we'll have this determinant greater than 0, and we will have a hyperbolic equation, which is the case for supersonic flows. So you can see, depending upon the value of this Mach number, the entire nature of the equation is changing. And what the implications of this is that the we will learn this in subsequent lectures, that there are different ways of solving parabolic and elliptic and or hyperbolic equations. So depending on the nature of the equation, the way we solve it is different. So in a case where this Mach number can change of a flow, uh, in such a situation the nature of the PD itself is changing, and so we have to make sure that our solution procedures are, versatile enough to take care of all the three scenarios, or at least the scenarios which can be possible in a given physical system, right? So the correct answer to this would be option D, of course, any of the above, depending on the value of Mach number. But these are the underpinnings of it. So any questions on this? Okay, if not, let's keep moving along. We'll move on to the sixth question now, which is again asking us to classify another well-known equation known as the trichomy equation. So, is the trichomy equation hyperbolic, elliptic, parabolic, or any of the above? Okay, we have one quick response in favor of option A. Option A again. So this is the general form of the trichomy equation. Now there can be variations to it, like I can keep the same thing and make it minus. So I could have dou to u dou x squared equal to minus x dou to u dou y squared. This is also the trichomy equation. Then instead of x I can have y as well. So I can say this is also a form of a trichomy equation, and this could be negative as well. Anyway, doesn't matter. So this is the general form of the trichomy equation. Like, let's take the simpler form for this. So if we try to mathematically classify this, what should it be? Should it be a hyperbolic, elliptic, parabolic, or any of the above? We have two responses in favor of option A. Let's see what others have to say. So if I try to classify this, what would my determinant be? B square minus 4AC. So B as usual is 0. I have 4. A is 1. And C is minus X. Right? Because this is on the other side. So if I rearrange this, this is what the equation would look like. So A is 1. C is minus X. And B is 0. So my determinant turns out to be 4x. Now depending on the value of x, I can again have three possible scenarios. So if x is less than 0, I can have elliptic. If x is equal to 0, I can have parabolic. And if x is greater than 0, I'll end up with hyperbolic. So here again, depending on the value of the uh, coordinate x, my equation turns from elliptic to parabolic to hyperbolic. So this can again be option D, any of the above. So any questions on this? Okay, if not, we'll keep moving along. Let's move on to question number 7 now. So there are 4 statements given here. You have to find the incorrect statement. So the first statement is that an equation is called elliptic if all the eigenvalues of A are complex. So these are related to, if we try to write a set of linear equations into a matrix form. So we looked into this in the second lecture. So let's say if I have a set of two linear equations which look like this. So if I have dou u dou t plus a dou u1 dou x, I'll call this a1 plus a2 dou u dou y plus a3 dou v dou x plus a4 dou v dou y equals 0, and another equation where I'm looking at dou v dou t plus b1 dou v dou x plus, or no, I'll follow the same pattern. So b1 dou u dou x plus b2 dou u dou y plus b3 dou v dou x plus b4 dou v dou y equals 0. So this set of linear equations can be uh, written in a matrix form where I write this vector u as the vector of the two different variables u and v, and the coefficients can be wrapped up into two matrices as well, where this is how I can write the matrix A as a1 a2 b1 b2, and another matrix B as a3 a4 b3 and b4. So in this way I can write this whole set of equations in a sort of a shorthand, where I can write dou u dou t plus this matrix A. Let's write it this way so that our options are consistent. uh, Option A dou u dou x plus b into sorry plus matrix B into dou v, sorry, there's no v, there's u dou y. I guess the coefficients will be different for this. Let me check this out. So for x, it would be a1 b1 and a3 b3. Sorry, and for y, it should be a2. For y, it should be a2 b2 a4 b4. Yeah. So this is a shorthand way of writing a linear set of differential equations. So in this case, the coefficients, in turn, the matrices A and B, they can tell us whether the equation can be mathematically classified as elliptic, hyperbolic, or parabolic. So read the statements carefully. There is one wrong statement among them. The first statement is that an equation can be called elliptic if all the eigenvalues of A are complex. Equation B, statement B says that a equation is called hyperbolic if all eigenvalues of A are real and distinct. And option C is telling that a equation is called parabolic if all the not all, if the eigenvalues of A are real but less in number than the number of PDEs. So less in number simply means that there are repeated eigenvalues. And option D is none of the above, which means that all of the three above statements A, B, and C are correct and none of them are incorrect. Okay, so we have a response in favor of option D. Let's see what others have to say. Option D again, good. Anyone else? So depending on the nature of eigenvalues of A, the equation itself, the set of equations can be classified as what? Okay, so let's take a look at the solution. It is actually option D, none of the above. So all of you are correct. Uh, so if the eigenvalues of A are complex, they do mean that the determinant, the equivalent of determinant B square minus 4AC is actually less than 0. And in that case, the equation would also be elliptic. If the eigenvalues are real and distinct, that means that the determinant is positive, uh, greater than 0, real and positive. So in that case, they are hyperbolic. And if they are real but less in number, then that means that the determinant is equal to 0, and we'll have and our equation will then behave as a parabolic equation. So all these three statements are individually correct, and as a result, the correct option which you had to pick was option D. That is, none of the above are incorrect. Okay. Any questions on this? Are you guys familiar with finding eigenvalues of any given matrix? So let's say if I give you a very weird set of partial differential equations, can you find out the first the coefficients and then the matrix A and then the eigenvalues of them? Okay. So if there are no questions, we'll keep rolling. We'll move on to question number 8 now. So earlier we had to find the incorrect statement. Now among these we have to find out the correct statement. So this is with respect to the characteristic normal. So we have a characteristic surface and the normal to that surface is what is called the characteristic normal. And it can have two different components depending on the depending on the dimension that you're considering. And dimension here refers to the number of equations as well. So if there are n equations, it would be an n dimensional space. Anyway, so just to visualize, two dimensions are enough. So So these are all, if you see the broader picture here, so uh, there are different ways in which we can mathematically classify uh, partial differential equations as well as set of partial differential equations. So here the four statements are, oh, we are already getting answers. So we have one in favor of A and one in favor of C. No need to rush, guys. I mean, just read the statements carefully and try to pick out your correct option. So the first statement is, but yeah, if you're getting it correct, then all well and good. So the first statement is that if statements of the characteristic normal are real, then the equation is elliptic. Option B says that if components of the characteristic normal are complex, then the equation is hyperbolic. Statement C says that if components of the characteristic normal are real but less than the number of PDEs, once again, it sort of uh, corresponds to those repeated eigenvalues case. In that case, the equation is parabolic. Or is it option D, all of the above, that all these three statements are correct? So someone says that it's only option A that's correct, and we have another person saying that it's only option C that's correct. Let's see what others have to say. Here you have to find out the correct statement. Okay, so option C seems to be the favorable answer. Let's go and take a look at the solution. It is actually option C, so very good. So the first one, telling that if the components of the characteristic normal are real, them being real means that the determinant b square minus 4ac is actually greater than 0, and which corresponds to hyperbolic. So this statement is wrong. It won't be elliptic, it should be hyperbolic instead. Whereas if the components of the characteristic normal are complex, then the equation should be elliptic, not hyperbolic. So both statements A and B are wrong. Statement C, on the other hand, is correct. So if they are real but less than the number, then that means that the corresponding determinant would turn out to be 0, and in that case the equation is indeed parabolic. And option D would also be wrong, because all of the above can't be correct, because two of them are correct and only one is correct. Incorrect, two of them are incorrect and only one is correct. So option C would have been the correct answer. All right, good. So any questions up until so far? Okay, if not, we will keep moving along. We have now another question related to how would you classify the boundary layer equation for flow over a flat plate. So if I have a flat plate like this and I have some flow coming in at uniform velocity, then a boundary layer develops, right? So this would be a typical velocity profile. This is U. This would be my X. So this is a typical schematic of a boundary layer formation. So how would you classify that boundary layer equation for flow over a flat plate? Is it option A hyperbolic, option B elliptic, option C parabolic, or option D both, not both, A or C? So either hyperbolic or parabolic. We have a response in favor of option C, that is parabolic. Let's see what others have to say. Boundary layer equation is also second order differential equation that find out the nature. uh, we get parabolic. Yeah, it's not just a second order equation, it has to be parabolic as well. So let's take a look at the correct answer. It's actually indeed parabolic, and the form of the equation. So if we start out from the Navier-Stokes equations and simplify them for the boundary layer, we will eventually come down to what is known as Prandtl's boundary layer equations, which looks something like this. Right. So here it's a second order equation, and the only component that we have to consider is this one, which is C, and A and B are both 0. So if we try to find out the determinant B square minus 4AC, we would come down to 0 square minus 4 into A is 0 and C is nu. So ultimately everything becomes 0 and the equation becomes parabolic. So this is a very unique sort of a case where usually parabolic equations are associated with time marching problems, where time is the semi-infinite direction in which we march. But a boundary layer problem can also be cast as a time marching problem, where where these are my two uh, coordinates y and x, and let's say if I know the solution at a certain y, sorry, at a certain x, let's call it x1, then I can keep marching and add x1 plus delta x and find out the solution there, and I can move to x plus 2 delta x and then find the solution there, and keep going and get my solution for a infinite boundary layer. Here the marching happens in space, not a time marching but rather a space marching problem. Okay, any questions on this? Okay, if not, we will keep moving along, and we have reached the last question of today's session. So it's asking us that which of these characteristics, so it should be these, which of these characteristics apply to parabolic equations. So this is in regard to the domain of dependence and domain of influence. So for parabolic equations, do we have option A, semi-infinite domain of dependence and semi-infinite domain of influence, or do we have option B, infinite domain of dependence and infinite domain of influence, or do we have a finite domain of dependence and finite domain of influence, or is that I've just written all three incorrect statements and it should be none of the above? Which one do you think is it correct for parabolic equations? Okay, we have two quick responses in favor of option C. Let's see what others have to say. All right, let's take a look at the solution. Solution is actually option A, semi-infinite domain of dependence and semi-infinite domain of influence. So why is that? So basically, if we take an example, let's say dou t equal to alpha dou 2t dou x square, which is the 1D heat diffusion equation. This is a parabolic equation, right? And here If I try to find out the characteristic curve, this actually turns out to be 0. So in the xt plane, if I draw the characteristic, it's actually a flat line because the slope is 0 of dou t dou x, right? From here. So at any point P, the domain of dependence is actually for all time before this. So let's say if this was t1, its domain of dependence actually is any t less than t1. So T1 is sort of a bound, an upper bound, and in the uh, and there is no lower bound. It's semi-infinite in that direction. So semi-infinite, what does it mean? Like, so let's first discuss that. So let's say if I have something which is infinite in both directions, that if I go towards lesser and lesser values, then it's infinite there as well, and towards the uh, higher value side, it's also infinite. So those are uh, truly infinite uh, entities. Whereas if I have something like this, something like, let's say, uh, x greater than L, which means that in the x line I will have a lower bound at L, and anything greater than L is within my bound. So this is an example of a semi-infinite domain. So once again, coming back to our problem, so the domain of dependence is semi-infinite because it's t less than t1, and the domain of influence is also the entire region that is above t1. So after t1, so t greater than t1 is the domain of influence. So these are both semi-infinite domains for a parabolic equation. Now, for hyperbolic equations, in contrast, we have these, crossing lines which are characteristics. So, uh, for the wave equation, we have seen that these slopes are 1 by c and minus 1 by c, right? So here, for a certain point, there is a bounded domain of influence as well as a bounded domain of dependence. Sorry, I spoke the other way around. This one is influence and this region is dependence. And for elliptic equations, there there is no real characteristic line. So the entire domain is the domain of dependence, is the domain of influence as well for any given point P. So you can imagine, right? So let's say an example of an elliptic problem would be the steady heat conduction case. So there, if I disturb any point of the system, the entire domain would be affected by it. So the entire domain is within its domain of influence. On the other hand, if I change any part in any other in any portion of the domain, then that would have an influence on every single point. So for any given point, the whole domain is its domain of dependence as well. So it works both ways. So that's all for today's session. If you have any questions, please ask away. Otherwise, thank you for showing up today. We will meet again next week. I can't find Amaresh's reference book. Please provide reference book. Okay, I will take a look at it. Hold on. Hmm, was it given in the about the course? Yeah, these three are good books and references. There was one book by Professor Dalal as well. Let me see. Let me see if I can find it. Hmm. Okay, that was on fundamentals of convective heat transfer. Okay, so I don't think there was. So for now, just stick to these three books for references. Okay, so this one is a good book on finite volume method. You can see my screen, right? Oh no, sorry. Okay. Um, so I'll post this in the chat box. So this third book by S.B. Patankar, this is a good book on finite volume method, and the other two are also nice. They explore both finite difference and a bit of finite volume as well. For our course, we will uh, first start off with some finite difference methods, and then towards the end, we will learn a bit of finite volume method as well. So these books should be uh, useful. Yeah, they are in the section over there. Yes. And these should be enough. I mean, you won't need more. Any other questions, anyone? How to practice CFD problems. So there are two aspects of it. One is, of course, the practical use of CFD. So for that, you will need a software, and pick start off with simple problems like a 2D channel flow, then move on to an axisymmetric pipe problem, and so on. There are many different tutorials of them, and keep following them, and you know don't attack a very complex problem at first. Start off with simpler problems, and as you gradually build expertise, uh, try to solve more and more complex problems. And the other aspect of it, that is the theory and mathematical part, for that the assignment problems of the current course that you are doing, as well as you pick up these CFD books, they will have some exercise problems in their back as well. Try to read through them and only solve the ones that you find interesting. So there are uh, there are two aspects of it basically. One is practical CFD, and other is learning the math behind CFD. So it really depends on which area you want to focus on. Which programming is needed in ANSYS? So for ANSYS, no programming is needed upfront. So ANSYS is basically a commercial tool with a very nice user interface. You can click on buttons and control things, and there are drag down menus for choosing different options and all that. So there is no programming knowledge required for that. And if you want to write your own code, that's again a very good way of learning CFD. That is, you try to write some very simple codes using any programming language of your choice. It could be Python, it could be MATLAB, or anything else, or C++, whatever you're comfortable with. Art theory problems and software mathematics problems, yes, they are different. Like if you are trying to solve a very complex problem, you won't really write your own code. Like that's not the practical way of doing things. Other people have written very extensive and useful codes. We can just use them to solve the exact problem in need, but of course with the knowledge of the math behind. And for learning the math and implementing simple cases, we have to stick to very simple and doable problems. So as I said, these are the two different aspects of it. Does that answer your question, or do you have anything else in mind? Any AI driven enhancer, that's the talk of the town right now. So there are many ways of doing that, and we need to first learn the basics of CFD, then learn the basics of AI, then of course we can go into that. There are, if you follow literature, there are recent works which are trying to use data science to entirely replace the uh, math and physics that goes behind CFD. So we will try to the main philosophy there is that if I have enough data of fluid flow, then I don't need to know the physics of it. I don't need Navier-Stokes equations. I don't need CFD. Using the data itself, I can predict how the fluid flow and how the force interactions between solids and fluids would be, just from a data-driven perspective. Anything else? Okay, so if there are no questions, we will meet again next week. Okay, thank you. Good night. Bye bye.